It's the CSS blank tag, okay? Just in case you're slow this morning. All right. This is an extract from my dissertation research with Henry Thompson. He's my advisor. I've been at this for a while. The paper I wrote is fairly dense. The slides are fairly dense. Well, okay. Let's see if that works. Okay. Lower. All right. I can't do that. Here, how about that? Is that better? Yeah. Yeah? All right. Perfect. I've now mastered mics. And I tend to talk fast. So I've got dense slides. I talk fast. Let's go. So the Open Web Platform. You may have heard this term. You may have not. It's like a rebranding of the web browser. But I think it's a good idea because people don't think of the web browser as a platform, as a tool that you can use in other contexts. And what the Open Web Platform really means is sort of we take all these bits. We take the recommendations, the standards, the notes, algorithms, implementations, all these shared expectations. We treat them as a contract between the developers and authors. Right? That's the platform. And my fundamental question in my research was, okay, but why isn't there more scientific data on the web? Why don't we have access in the same way that we have access to other kinds of information, social networks, Twitter feeds, all these things? We don't have that kind of data. It's you go there, you get find some giant tarball of some stuff. Or does the web work for that? So, so I did a bunch of research on this, and I played around with different things. This is a wonderful pie chart of data that's stored at data.gov. It's a metadata repository. It points off into all these different places in the US that have, you know, the EPA, the NOAA, the National Weather Service that have data. And I specifically looked at geospatial data because it's easy to sort of equate that with something that might be scientific. And there's all kinds of things in here. You probably may not be able to read it because it's an image. But this part and this part are about 67% of the data, and that is tabular, right? It's either directly tabular data or it's vector data that contains tabular data. So there's I mean, scientists like to produce tables of data that are weakly related to each other. It's tables, reams after reams of tables of numbers, and they mean something. But the formats they use to distribute this information, they often predate the web. They're things that are proprietary formats like ESRI shapefiles. They don't work within the browser. They're FITS images. FITS images are a bunch of image data and huge tables of data stuck into an image format. They have archives of these things, but they're too large to be processed. If you go and look at the Sloan Digital Sky Survey, it's astronomers, it's a terabyte zip file, right? That's what you go download our data, terabyte. That'll take a while. And then who knows what it is, because they don't really tell you until you download it. So it's a real problem. These things are not on the web. And what I want to be able to do is, within the Open Web Platform, poke at this data, explore it. Henry's term for this is paddle around in the data, right? I like that. So I'm going to change the paradigm here. I want to have a methodology for getting data out onto the web. We want it to be accessible. We want to use web-oriented formats. We have tabular data. I've seen a lot of XML that looks just like an HTML table. Why do we have the same markup, slightly different over and over again? So why can't I use HTML tables? Well, there's lots of problems there. And people don't name stuff with URIs. They don't actually give you a constant, stable URI for something. The URI is a mechanism for downloading the data. So we like to name things on the web, make them identifiable so we can retrieve them, we can do stuff and make assertions about them. We need to name things. And you might be wondering at an XML conference, well, we should just be using XML. Why aren't we? Well, people have done that. Astronomers, interestingly, after doing the research here, have been using XML since day one, actually before that. And they've been using it for exchanging data. And they have a thing called VO table, and that is a almost copy of the HTML table model in their own namespace. And it has sort of worked for them, but it only really works in the sense of like tool-to-tool exchange. So when you hit one of these services and you bring it up in the browser, you don't get anything really useful that you as a random, say, amateur astronomer can use. And that's a real problem. I mean, you're not enabling people to do things with the data unless they have big infrastructure. So, we have some problems here, right? What are the problems? Well, data's too big, right? Real data sets, they're too big to actually operate on within the Open Web platform. They'll make your browser crash. So we need to solve that problem somehow. We don't have enough semantics. Scientific data, generally, there's things like, here's temperature that I measured in a particular way using a particular unit of measure. I have the error for statistical error for that. You have all this metadata around these numbers that are in these tables. And you don't really have that ability directly in HTML. And then there's this question, this particular viewpoint on this, but you know, we have some of these services like the IVA astronomer cone search services. You know, you create this big URI and you can get a piece of data back in XML. But formulating that URI is not so easy, and it also is sort of a temporal thing. It's not like that's a thing that I can name and then use in the future. How much I get back is limited. So this process of constructing names is very different from service to service, and it's very temporal in the sense that I can't get that, or maybe I have to page, or I don't know how much data I'm going to get back. So we have these three little pig problems. So this is my solution to this, and I call it PAN methodology for partition, annotate, and name. So we're going to partition the data, and we're going to figure out how to do that using properties of the data to create web-sized chunks. We'll talk a little bit about what that is. We want to annotate the data. So I want to be able to use a common syntax of the web, something that is already there, which happens to be HTML. That works really well in the browser, but it doesn't have the things we need. So we're going to add to it RDFa. And then we're going to name things, right? We're going to use the web architecture, you know, the way it has been described as the preferable methods of naming things on the web. You can go read this document. It's a W3C document called The Architecture of the Web, Volume 1. And it talks about naming and good mechanisms for naming. And you might think, well, this doesn't seem really overly complicated, but simple is good, right? We like simple. And people don't, in these communities, they don't think about data this way, right? They're thinking about, I'm going to make a query, and that query is going to return some amount of data, and maybe I have to page that, so they don't think about partitioning it in advance. But there are choices you have to make, and that's sometimes hard. They don't necessarily annotate. The astronomers did a little bit of experimentation with that. It didn't really take off. So this is new. What do we do with that? Whose ontology do we use? And there's some good work in that. NASA did a whole ontology for quantities and units of measure. Fantastic stuff. Really well, a good proposal, but I don't think anybody's using it yet. And then, of course, when you have fixed partitioning, you have to have stable URIs. There's a whole aspect of that as well. So what I mean by partitions? It's awful small. You can't see any of that, can you? Let's try blowing it up. How's that? Feel better. So a lot of these data sets, like the stuff I'm going to show you in a bit, it's time series geospatial data, right? So we have these different natural dimensions of location and time. And you can think of this large data set as being chopped up into little pieces along those dimensions. We carve out spaces that there might be data. So these boxes could or could not be filled with data, right? You could make a pick a coordinate in space and time, and you might not have data, right? And you may have data. So those partitions, are sort of dependent on your data. But we're going to give them all names. They are all addressable, right? Whatever scheme you come up with, naming your partitions, you're going to be able to address all of these things regardless of how much data is actually there. Now, it might seem kind of silly, but it's actually really good for open-ended time series data. It makes a uniform architecture, and there are ways to basically produce marginals, summaries, that tell you where there is data. So for example, an astronomy service might say, I have this particular region of the sky, and I have data for these things, and I have this much data within each of the partitions. So those kinds of marginals are very useful. I think I need to make this smaller again. Yes. So what do I mean by annotations? RDFa. There you go, right? In HTML, it can get a little verbose, but it's useful. And the main event for me is this HTML table. We have tabular data. We have the HTML table. What are we going to do about adding to that the semantics that we need? Well, I took a partial annotation model here. I don't want to mark up every single table cell because that would be a lot of extra stuff in there. So taking, sort of doing similar things to what the IVUA did, the Astronomers Standards Organization, they just talk about the columns of data. They just describe the header of the table. So here we have a table head. We're describing a single column in this table. It happens to be air temperature. Here's the NASA QDOT stuff. There's thermodynamic temperature in Celsius. There's a data type, so in the programming language, it's a double. There's the symbol for Celsius, et cetera. So I have a bunch of information about that. But the location, right, in this table, this needs to be very regular. The location in the header is the same location that in a particular role. So I can look at this thing and go, oh, the fourth column is air temperature, and here's the fourth column in the row, and it's 22.2 degrees Celsius, right? And I know that it's Celsius by looking at that table header and lining things up, right? Not generally rocket science, but it's a partial model. If you get the RDF out of this, you're not going to have any of your data, just the metadata about the table. But we can annotate all kinds of things in that partition. One of the really useful things is links. So this is a link with a lot of information packed in it. It's a link to a partition that's nearby. So in that picture that I showed you of all the boxes, right, it's the web. So partitions can link to each other, and that's a really useful feature. Well, how do they do that? How do I know what's that thing's a link? Well, we have to type it, type of partition. We have to assert some information about that partition. Now, this one is a nearby partition. So these two giant pieces of spans tell me that this is, in fact, a different quadrangle. That's the top one. It's geoshape of a schema box. I'm using schema.org stuff there. And then down below here is the time period that it's for. So it's from these two different times and on the 12th, and the period of time is 30 minutes. And this information gives me some aspect of those facet dimensions. Now, the facet property in both of these things is telling me something about these partition properties I picked out. How did I partition my data? So there's a little bit of cart before the horse here in the sense that if you're processing a particular kind of data, you need to know how it was partitioned. Right? There's some extra sort of metadata there. You know which choices you made. So latitude and longitude and time is the way I'm partitioning this. So I've actually done this. I've used it. You can't see that picture in the bottom, but I'll start with the top. So I actually found some good time series geospatial data called the Citizen Weather Observation Program. It's people who have weather stations. I put one up in my backyard to test this. And they spit out data onto the web. And what they spit out is this. It's some crazy ham radio protocol from back in the day that they put on the internet using their own home-cooked peer-to-peer system. It's weird. And I take that and turn it into something else, XML. Go figure. But I get about 53 million weather reports a month. Generates 12 gigabytes of data per month. And let me just zoom this up, make my plug for MarkLogic here. I don't work for them, I'm just a groupie. But I take this stuff off this crazy APRS wire, turn it into XML, use XProc, stick it into MarkLogic, use all the geospatial features, and I use XProc to get it out and turn it into web pages and to serve up all that data. Works really well. XProc and MarkLogic get along quite well. So, there's an aspect of this that, why would I be using HTML with RDFa to do this? And I think the aspect, well, the thing that strikes me, and I'm going to show you an example here. It's just loaded. the data has a duality. It is a web page. There's a nice visualization of the weather in the Bay Area right now, I think. No, actually on the 12th when I wrote this. And if you scroll down, there's a giant table of data. There's all the weather reports. But that visualization was generated by looking at the page. So the page is looking at itself and generating the map and plotting, putting all of the temperature and coloring it. And there's a little statistical thing up there about the temperature. All that's generated dynamically on the client by looking at it, the document itself, and where is the data, right? It's not in JSON, it's not in some other format, it's just in that HTML table. I'm looking at the annotations, and I prove that there's some annotations in here. If you really want to, go to the console, and I'm going to just document data, graph, toString. There's a bunch of RDF triples, and I can't even read it here, so don't even try. But it goes on and 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 on. There's a lot of metadata in here, and there's a lot of all that information about the table columns as well. So this is just a simple example of the page. It's just a regular web page, but it's also data, right? I can do something with it. You see one example of that there, and we're going to do more with that. We don't use JSON. We don't do that. Good. So I have these partitions. I have web pages. What can I do with them? Well, this is where you need to get creative with your partitioning and what you do with them and your naming. So I came up with this idea of sequence numbers. Basically, you partition the world into quadrangles, and you just number them. And they have start at the top, all the way around, counting. They have a nice property that you can calculate, use this nice formula to generate the sequence number from a location. And the other nice property is that if you have some kind of polygon that you're trying to, some area you're interested in computing something for, you can take the bounding box of that, and you can generate the sequence numbers that are going to cover that of the quadrangles that you need. And if, in my case, the way I did this, sequence numbers are embedded in that URI. They're a piece that I put into the URI, and so I can use those things to generate the URI of the partitions that I need to start with. So I take the one extreme end of the time period I'm interested in, take the set of sequence numbers, and I can generate a set of partitions. Well, I have links in these pages, right? So I can look at those links, and I can go backwards and forwards in time. So you can create a backtracking algorithm where you start with one set of partitions, and then you just follow the previous links until you've gone to the end of the time period you're interested in. It makes a nice, efficient way of traversing these data partitions. So you have a basis for good algorithms. So when we get to those partitions and we want to do that, how do we find the data? Well, obviously we write some JavaScript, because that's what we do on the web. We write piles of JavaScript. And there's an API for RDFa. It's now published as a note. They didn't want to make it a rec for one reason or another. It's OK. I added some things to it that you need. So someday we'll have an official API, I think. And what you do, basically, is you have the annotation graph and you have the document. Well, every triple in that annotation graph has a location in this document. And so you can go into the annotation graph and find something, and then go to the location in the document and find something, and go back and forth. So if I want to find the table of data, I go into the annotation graph, I find the things that are typed of partition, and then I find the location of that. Well, that's the partition in the web page. I use the subject of that to find the item. In my ontology, I have an item thing that points to something that's in the partition, which happens to be a table. So now I have the subject of the table, and then I find the location of that subject in the document, and now I have the HTML table element that I need to process. And so I do a lot of this. I go back and forth between the annotation graph and the document using the JavaScript API. I showed some versions of that for other purposes last year in the talk that I gave as well. Hopefully it makes more sense this year. And it looks like this, and we're going to skip this slide, but those 3 steps are 3 steps and 3 lines in JavaScript. When you want to find the column, it's a few more lines of things, and you can find the index of the column in the table. We're going to skip that slide for now. So we can process data. Now we can traverse the partitions. We can do things with it. So what will we do? Well, we're going to do MapReduce, because MapReduce is what people like to do with big data. So what we're doing is we're taking the partitions and we're processing them. We're treating them as the resource that we're processing. We're turning that into some resultant. We're applying a function to the partition, generally speaking, to the document. And we're getting a resultant, whatever we want it to be. And then we're reducing those resultants, right? So that's general MapReduce process. But we're going to do all of this in the browser, right? And the interesting thing about this is that because we have stable partitions, we have stable names, we generally have resized the partition to something that is processable in the browser, we're not going to get stuck. We're not going to produce, run a query that gets too much data and then we crash and burn. Or we're not going to get stuck behind the next request because we have to page, right? We can do this in parallel. We can use whatever parallelism the platform is going to give us, which isn't a lot, right? There's only one thread in JavaScript. But we can interleave things, and it works okay. Is that what's really next? Oh, yeah, so here's my math slide. So we're going to do something real. There's this thing called Barnes interpolation. It's a climate scientist of sorts. They didn't call themselves that back in the 60s, named Barnes. Came up with this. It's an interpolation process means that given a small set of values, I'm going to generate a bigger set of values, right? So if I have a set of weather observations like temperature for discrete locations, and I want to get a bunch, sort of assume what the temperature might be elsewhere where I don't have a weather station, that's what you use this interpolation process for that. It's a weighted average. And the weights are based on distance. They get recalculated at each stage, and you just basically iterate until you are within some tolerance of your observed values. So you apply this some number of times. It turns out that you need about 3 iterations and you're done. So what does it produce? It's the typical thing you see on the news, the nice, sort of temperature gradient colored on your map, right? That's what they use this for. He did this back in the early 60s on an IBM mainframe. We should be able to do it in the browser. And the process looks something like this, the MapReduce process. We take a region of the world that we're interested in for a time period. We have this theoretical set of partitions, right? And so we process these by traversing them. We get a grid average, a sparse grid of observed values in, the average of the observed values within that grid. So what I mean by a grid is that we're going to divide this space into something like if we are processing a 10 degree by 10 degree quadrangle, we might divide that into 1 degree squares or 1/10 of a degree squares. Right? And then whatever occurs in those little squares, we're going to take the average of. We get a sparse grid. And then we run the interpolation process, and we have filled that grid up with numbers. And then we do something with it. We turn it into a picture, which we can do. We're going to do that right now. So here I've selected the Czech Republic here, right around us, basically. That's not the whole Czech Republic. I'm going to use a 1/10 of a degree. It's for this morning, a little bit. We're going to use 30-minute duration. That will pull one slice, one set of partitions for that area. We're going to color it from -10 degrees Celsius to 37. And we're going to use 2.5 degree partitions. And we'll just hit calculate and see what happens. All right, done. So what happened, right? If you want to see, there's the picture. You can kind of see the little grid lines in here. And you can do it on the map. I can't really see the map that well, I guess, but there it is. Well, we retrieved the partitions. There are, let's see, 4 of them? No, there's more. There's more than 4, but there's 4 there. I do 4 at once, so 4, 5, 6, some more of them. Each of these partitions, I've packed into the URI. This is the naming part, right? The 2.5 here is let me blow that up. You see that? My slides are obviously not meant to do that. 2.5 degrees, I put that in there. This is the sequence number. There's a date time here, it's tacked on the end. All this information about that partition the metadata is packed into the URI. There's a regular way for formulating that. So when I get my sequence numbers and I know the start period, I formulate this URI, start there, and then I can follow the previous links backwards. It's very short, and then it was 1.2 seconds to do that. What happened? Well, it loaded an XHTML document, did all the RDFa processing to make the triples available, and did that back and forth, and found the temperature column, and then processed it, and generated the sparse grid, and did all of that in 1.5 seconds from XHTML data. It's very tractable, right? It is completely reasonable to do this with XHTML and RDFa. You could substitute XHTML with XML and random choice of yours. It's going to give you the same metric, right? Because the time occurred is to navigate, via your scripting language, in this case JavaScript, to navigate between the annotation graph and the markup. So my choice of markup is just because I can go to that partition page and view it, right? I don't have to have special software. The browser does it. It does something useful for the random consumer. Well, so you can actually scale this up. Now let me close this for now. So here is the polar vortex, favorite word right now. On January 23rd, for the whole United States, purple is really cold. Purple is like minus 20 or 30, actually more like minus 30 Celsius. So like up in Minnesota, where I'm from originally, people living in my hometown, minus 30 Celsius, right? This is the polar vortex that's been taking over the United States. This took 22 seconds to render in the browser. It's 240 partitions. It's a 1/4 degree grid. So it's very tractable. Right? You can actually do this in the browser. So, would you do this as a scientist? Well, I can run headless browsers now. So I can take things like Phantom.js and run WebKit, what's inside Safari, from the command line and generate this picture if I want to. And so I did some of this. I didn't use Phantom.js. I just sat in front of my browser and ran it several times. We can animate that. So here's the polar vortex for the whole of January. The data here was generated by processing all those XHTML pages, loading all that data. It was, I did it over, for every day, I did it every 4 hours for a 30-minute period. So these are 30-minute snapshots every 4 hours over the whole period of January. I find out interesting things about this, like the browser eventually slows down, right? It leaks memory like you wouldn't believe. So, eventually, if you don't, on my older laptop, well, I kind of had to close the window and open it again after doing this n number of times. On my new laptop, I have a lot more memory. It doesn't do that. So this is network bound, right? So the data access is the biggest part of that. So 2 minutes, all right. Good, because that will just keep going. Because this is my last slide. I did it. So why would you want to do this? Well, because people can just look at what I did. They can open up the browser and do view source and go, here's the JavaScript that did it, and there's what the markup looks like, and I can do this for myself. And this code, Henry keeps telling me that this is Tim Berners-Lee says this. Can't find this anywhere, right? But, I like it, right? Can't underestimate the power of view source. You can just look at what you did. It's open, it's there, it's available. Copy it. So I call it copy and modify. Took your stuff, tweaked it to do what I wanted to do, right? Now it does good things for me, right? And this lets good constructs go viral, bad things go viral as well, but whatever. But it enables a hacker in the corner to do something good with data. We want them to do that with scientific data, right? We want to lower the cost of doing this. We want to enable citizen scientists, all kinds of good things. So that's the point. And I'm done. This is one, right?
Thank you. Thanks, Alex. And I can see you want to raise a hand. Michael.
Thank you very much, Alex. Very interesting. 2 questions, I think. You may have addressed either or both of them, but You were going kind of fast sometimes. So when
I
you
did
did your
go on.
search,
Yes.
when you did the live demo, you had a sort of standard search interface. What do you do if the user selects values that don't correspond to the partitions that you've made? Are you partitioning dynamically, or?
Well, in my case, it's a time series. It's time series data, and you can ask for things that don't exist, and you'll get a table with nothing in it. You always get a response from my particular system. I've designed it that way.
Okay.
Right? But you could ask for nonsense, and then it's just going to halt and catch fire in some way. Like you could ask for a location, values of, locations that don't exist. 500 degrees latitude. That won't work.
Okay.
Right? You're not going to get a result for that. That's a bad request.
When I think about how to apply this to projects I'm working on, I realize there seems to be one crucial difference. I have been thinking, encouraged by the other people in the projects, that what they are looking for are very special cases, and we may need sort of arbitrarily complicated queries. Rectangular slices seem not to be quite the way to do this. To apply it to your case, I'm imagining how would this work in the case where someone studying the weather data says, no, I really need to look at just those days when northern Arizona is colder than southern Illinois. Does that map to your model at all, or is that a different problem to which this is not a direct solution?
Well, the process of getting the right partitions is there's a whole another layer here of the geospatial computations, right? If I have some random polygon, right, and I want to know what data is inside that, once I get the partitions back, I have to then go, is this piece of data in the polygon that I'm interested in? So that's a problem, but that's a geospatial computation problem that every system has. And all I'm saying is that you can get coverage, and then you have to compute that, right? So if you're saying compare region X to region Y, you have two polygons. You have to cover them, get the data, find the ones that are inside the polygons, and then do your computation, which happens a lot anyways. If you're the astronomers have this problem too. You can say, give me all the data in this cone. You're going to get lots of data you don't want, and then you have to filter it somehow.
Okay, so your model is the partitions is the first step. You bound it so that you need to transfer a minimum amount of data, and then you will have arbitrarily complicated querying and filtering happening in the browser. Right. And that's just the second stage. Is that?
Right. The fundamental problem right now is access to data. We don't have data on the web. So the idea of the methodology is we provide this. Now, if you're trying to do high-performance modeling of hurricanes and stuff like that, you're going to have to take the data out of this system, put it into your high-performance grid thing, and run your simulation, right? People do all that already. That's the high end of computation. You just saw the other end of it in the browser. So there's a spectrum here. I'm trying to sort of get the middle to bottom spectrum solved. Because the big guys already have money and time and systems.
Okay, thank you. So thank you, Alex. We need to continue with the next presentation.